A major multinational bank recently funneled $20 million into a flagship customer service overhaul, intending to leverage generative AI for everything from account queries to loan risk assessments. 6 months later, the project collapsed. Why? They hit the invisible wall. They attempted to use LLM's probabilistic engines to solve deterministic loan default problems that required traditional machine learning. This wasn't just a budget oversight. It was a fundamental failure in architectural classification. When you treat GenAI as a silver bullet for problems that actually require structural data modeling, you invite massive latency, soaring token costs, and a complete lack of explainability. In the world of information engineering, this is known as conceptual debt. If your initial categorization is wrong, every subsequent decision from your vector database selection to your GPU provisioning is a step toward failure. By the end of this lecture, you will possess the diagnostic framework to prevent such architectural catastrophes. Technical debt is often discussed in terms of messy code, but in AI, the deadliest debt is architecture rigidity. When an architect fails to distinguish between deep learning and standard machine learning, they lock the organization into rigid, high-maintenance data pipelines. Imagine building a massive 100-node GPU cluster for a problem that could have been solved with a simple XGBoost model running on a standard CPU. This happens because stakeholders chase the GenAI buzzword without understanding the hierarchy. You end up with an infrastructure that is too heavy to pivot and too expensive to scale. The invisible wall is that point in a project where you realize your data ingestion layer doesn't support the specific training needs of the model you chose, because the fundamental definitions were blurred. This misalignment creates a bottleneck that no amount of additional funding can fix. But how do we move from diagnosing failure to ensuring mastery? Let's look at the specific skills you are about to acquire. To overcome these walls, you must think like an information management professional engineer. Mastery in AI doesn't mean knowing how to prompt. It means knowing exactly where a technology sits within the ISO/ISC 27989 standard and the NIST AI risk management framework. In this lecture, I will equip you with a 2026 Taxonomy, a future-proof mental model that allows you to categorize any emerging AI technology instantly. You will learn to evaluate fitness for purpose. Whether it's a transformer-based model or a traditional recurrent neural network, you will understand the underlying data requirements and the compute trade-offs. This clarity is what separates a prompt engineer from a systems architect. You will gain the ability to justify your tech stack to a C-level board by demonstrating a clear alignment between business logic and the AI hierarchy. The roadmap is clear, but the terrain is often misunderstood. Let's look at the first map of this territory. Let us establish the foundational map. AI is the umbrella, the broad discipline of creating systems that simulate human intelligence. Within that, machine learning is the engine, focusing on algorithms that learn from data without explicit programming. Narrowing down further, deep learning is the specialized core, using multi-layered neural networks to mimic the human brain's processing. Finally, generative AI is a subset of deep learning, specifically designed to create new content rather than just classifying existing data. Most practitioners see these as separate, competing bubbles, but the true architect sees them as nested dependencies. You cannot master GenAI without understanding the DL layers it sits upon, and you cannot deploy DL effectively without the foundational data principles of ML. This hierarchy looks simple on paper, but in Chapter 2, we will decouple these layers to reveal the hidden complexities that even senior developers often miss. In the early days of enterprise computing, artificial intelligence was synonymous with expert systems. Architects designed rigid if-then logic structures to simulate human expertise, a paradigm known as symbolic AI. From an information management perspective, this was highly deterministic but suffered from extreme brittleness. If a scenario wasn't pre-coded, the system failed. This is why many legacy AI projects in the 90s remained proof of concepts. We must understand that AI is the broad umbrella for any technique that enables computers to mimic human intelligence, whether through hard-coded logic or advanced statistical models. In modern architecture, we are moving away from this manual rule setting towards systems that evolve. But how do we bridge the gap from rigid rules to fluid adaptation? The answer lies in the shift toward data-driven logic. Question: is it possible for a system to learn the rules itself without a programmer writing a single if statement? Machine learning represents a fundamental decoupling from explicit programming. Instead of an architect defining the path, we provide the algorithm with a goal and historical data. As Tom Mitchell famously defined it, a computer program is said to learn from experience E with respect to some task T and performance measure P. In the field, this means our focus shifts from coding logic to feature engineering, the art of selecting the right variables for the model to process. This transition is what allowed for breakthrough applications in fraud detection and recommendation engines that simply couldn't be mapped out with manual rules. However, the architect's role becomes more complex as we manage data quality instead of just code quality. Payoff: this transition isn't just a technical change, it's a shift in how we define the truth within our data architectures. To manage machine learning effectively in an enterprise framework, we categorize it into 3 pillars: supervised, unsupervised, and reinforcement learning. Supervised learning is the workhorse of the industry, used for classification tasks like credit scoring or regression tasks like price forecasting. Unsupervised learning, on the other hand, finds hidden patterns in unlabeled data, which is essential for customer segmentation and anomaly detection in cybersecurity. Finally, reinforcement learning focuses on optimization through trial and error, often seen in high-frequency trading or logistics robotics. Understanding these categories is critical for information management professionals when selecting the right technical stack for a business requirement. Teaser. But even with these pillars, traditional ML hits a ceiling when faced with massive, high-dimensional data, which leads us to the deep learning revolution. Deep learning is a specialized subset of machine learning that utilizes artificial neural networks with multiple hidden layers. From an architectural perspective, the deep learning refers to these layers which allow for automated feature extraction. In traditional ML, a human expert had to tell the model which features like age or income were important. In deep learning, the network itself discovers the hierarchical features within the data, starting from simple edges to complex concepts. This mimics the human visual cortex and is why DL excels at tasks that were previously impossible for standard algorithms. It's not just more layers. It's a fundamental change in how we process information complexity. Question: why did we have to wait until the 2010s for this technology to dominate if the math had existed since the 60s? The reason deep learning succeeded where traditional ML reached its limits is the performance paradox. Traditional machine learning algorithms follow a curve where performance plateaus as you add more data. The model simply becomes saturated and cannot learn more. However, deep learning models, especially large-scale ones, follow scaling laws. Their performance continues to improve as you feed them more data and increase the number of parameters. This is the core justification for the massive investments we see in modern AI data centers today. As architects, we must recognize that for certain scales of data, traditional ML is no longer a viable option. Payoff: this scalability is exactly what paved the way for the massive language models we use today. Finally, we must look at the infrastructure that enables this hierarchy. Deep learning is specifically designed to handle unstructured data, images, audio, and large-scale text, which accounts for over 80% of modern enterprise data. This transition required a move from CPU-centric processing to GPU and NPU-centric stacks capable of massive parallel matrix multiplications. When we build an AI architecture today, we are managing a stack that starts at the hardware level with specialized compute, moves through the DL framework like PyTorch or TensorFlow, and ends at the application layer. This foundation is what allows us to move beyond simple prediction into the world of creation. Bridge: now that we've decoupled AI, ML, and DL, we are ready to explore the most significant shift in the last decade, generative AI, and the total transformation of the AI hierarchy. In traditional enterprise AI, we spent decades perfecting discriminative models. These systems are designed to model the conditional probability P I X, essentially asking, given this input data, what is the most likely label? Think of an insurance fraud detection system or a credit scoring engine. They draw a boundary in the data space to separate normal from anomalous. However, the paradigm shift occurs when we move to generative AI, which models the joint probability distribution P(x). Instead of just drawing a boundary, it learns the underlying structure of the data itself to generate new instances that could have originated from the same distribution. This shift from classification to creation is what separates a predictive tool from a cognitive partner. If your architecture is still built solely on discriminative logic, you are missing the capability to synthesize solutions. But how exactly does a machine create something that looks original? The secret lies in how it maps the entire universe of data into a hidden mathematical territory. To understand the generative in GenAI, we must master the concept of the latent space. Imagine a high-dimensional mathematical space where every point represents a potential piece of data. During training, the model compresses massive datasets into this space, clustering similar features together not by literal appearance, but by semantic meaning. Content synthesis is not copy-pasting or searching. It is the process of navigating this latent manifold and sampling a point that hasn't been seen before, but follows the statistical rules of the training set. This is why an LLM can write a poem in the style of a technical manual. It is interpolating between two distinct regions in the latent space. From an information engineer's perspective, this is a transition from data retrieval to semantic inference. But this high-dimensional navigation requires a specific engine to manage the sheer complexity of relationships. Let's look at the specific engine that made this leap possible. The dominance of generative AI today is inextricably linked to the transformer architecture introduced in the Attention is All You Need paper. Unlike previous recurrent neural networks, RNNs, that process data sequentially, the transformer uses the self-attention mechanism to process entire sequences in parallel. It assigns different weights attention scores to different parts of the input, regardless of their distance. This allows the model to understand context and long-range dependencies that were previously impossible to track. For an architect, the transformer is the ultimate scaling engine. It turned the AI problem into a massive compute and data scaling problem, leading to the large language models we see today. However, simply having a powerful engine isn't enough for a business. We need to categorize these models to understand where they fit in our 2026 enterprise roadmap. Do you know which modality will drive the next wave of ROI? As we look toward 2026, the GenAI ecosystem has matured into a multimodal landscape. We are moving past simple text-based LLMs like GPT-4 towards large multimodal models LMMs that natively process vision, audio, and code. In the enterprise space, we categorize these models not just by their size, but by their modality capability. LLMs handle the logic and reasoning, diffusion models dominate visual synthesis, and specialized code models drive the SDLC automation. The architectural challenge now is orchestration. How do you pipe the output of a vision model into a reasoning model to automate a complex business process? Understanding this matrix is the first step in avoiding the one-size-fits-all trap. But even the best model is useless if it doesn't know your company's private data. How do we bridge that gap without spending millions on retraining? In practice, implementing GenAI follows a clear operational hierarchy. It starts with prompt engineering, optimizing how we query the model. When that isn't enough, we move to retrieval augmented generation, RAG, which connects the model to an external vector database of your enterprise's private documents. RAG is the gold standard for 2026 because it grounds the model in facts without changing its underlying weights. If the task requires specialized style or deep domain terminology, we look at fine-tuning. Only in the most extreme cases do we consider full pre-training. As an architect, your job is to select the lowest cost, lowest risk method that achieves the required accuracy. But wait, even with the best RAG setup, these models are probabilistic, not deterministic. This leads to the most significant risk in modern AI, the tendency for a model to confidently lie to your face. Hallucination is not a bug, it is a fundamental characteristic of how LLMs work. Because they predict the next most likely token, they can prioritize grammatical fluency over factual truths. In an enterprise environment, this is a critical failure point. We solve this by building safety rails and verification layers. This includes semantic guardrails like NEMO guardrails or Llama Guard, and architectural patterns like chain of verification. We must treat GenAI as a probabilistic engine that requires a deterministic wrapper. As we conclude this chapter on the GenAI paradigm shift, remember that technology is only half the battle. The real challenge is integrating this into an enterprise strategy that doesn't just chase hype, but delivers measurable value. In the next chapter, we will look at the enterprise adoption strategy to turn these concepts into a production-ready roadmap. In the enterprise world, AI is not a standalone toy. It is a complex organism that must live within a hybrid cloud reality. When we look at a mature architecture, like those modeled by IBM's Watsonx framework, we see a clear separation of concerns. At the bottom, we have the data layer, the data fabric that abstracts away whether your data is in an on-prem DB2 or a cloud-based S3 bucket. Above that sits the model layer, where foundation models are managed and served. The critical error most architects make is jumping straight to the application without securing the middle layer, the AI governance layer. Without a unified stack that handles data lineage and model transparency, your enterprise AI will remain a fragmented series of shadow IT projects that never scale. We must move from siloed deployments to a governed, layered approach that ensures every token generated is traceable and compliant. But how does a raw dataset actually transform into a governed service? The workflow is more rigorous than you think. Moving from a raw dataset to a production-ready AI agent requires a specialized lifecycle, often referred to as LLM ops. It starts with data curation, where we filter for quality and PA. Then comes the model selection, choosing between a massive proprietary model like GPT-4 or a highly efficient, fine-tuned open-source model like Llama 3 or Granite. The third step is tuning and alignment, where techniques like FT, supervised fine-tuning, and RAG, retrieval augmented generation, are applied to ground the model in your specific corporate knowledge. Finally, we reach the monitoring stage, which is the most overlooked phase in the enterprise. Here, we track hallucination rates and drift in real time. If a model starts giving inaccurate financial advice, the governance system must be able to trigger an automatic rollback or a human intervention. This process ensures that AI isn't just powerful, but predictable. However, even the best process fails if you haven't checked the legal and privacy boxes, the silent killers of enterprise AI. As an information management professional, your primary duty isn't performance, it's risk mitigation. To deploy AI in a regulated industry like finance or healthcare, you need a strict architectural checklist. First, is there a zero data retention policy with your API provider? Second, does your RAG system respect existing ACLs, access control lists? Or can a junior employee query sensitive CEO-only documents via chatbot? Third, how are you handling the intellectual property of your prompts and tuned weights? We often see shadow AI where employees leak proprietary code into public LLMs. Your architecture must include an AI gateway that acts as a firewall, inspecting outgoing prompts for sensitive data and intercepting toxic responses. If you can't check these boxes, your project will be killed by the legal department before it hits production. Now, assuming you have the governance settled, we can look at the next evolution of this hierarchy. Systems that don't just talk, but actually act as autonomous agents. The most significant shift in the AI hierarchy today is the move from generative AI to agentic AI. While GenAI focuses on creating content, agentic AI focuses on completing tasks. This is the difference between an AI that tells you how to book a flight and an AI that actually books the flight, manages the budget, and sends the calendar invite. This requires three core capabilities: reasoning, planning, and tool use. Using frameworks like React, reasoning, and acting, these systems break down a complex goal into a series of subtasks. They can access external tools like Python interpreters, SQL databases, or ERP APIs to gather information and execute changes. We are moving away from a chat interface toward action interfaces. This is where the true ROI of enterprise AI lies, in the automation of multi-step cognitive workflows. But wait, is every advanced chatbot an agent? Many people confuse the two, and that's a dangerous architectural mistake. Let's clear up the confusion. A chatbot is reactive. An agent is proactive. A chatbot follows a linear conversation path, often using array to provide better answers. An agent, however, has agency, the ability to decide which tool to use and when. Think of a chatbot as a librarian who helps you find a book, whereas an agent is an executive assistant who not only finds the book, but summarizes it, checks your schedule, and schedules a meeting to discuss it. Architecturally, chatbots are usually stateless or have simple memory, while agents require a scratchpad, a long-term and short-term memory system to track the status of their ongoing plans. In an enterprise setting, deploying a chatbot is low risk, but deploying an agent that can write to a database requires an entirely different level of security and human-in-the-loop oversight. The real danger isn't the agent failing, it's the agent succeeding in a way that violates your business rules. How do we manage this autonomy? The future of the IT professional is not as a builder of code, but as a director of agents. In this new paradigm, we use human-in-the-loop (AITL) architectures where the AI proposes a plan and the human approves the critical execution steps. This creates a collaborative ecosystem where humans focus on high-level strategy and ethics, while agents handle the high-volume, repetitive cognitive labor. Imagine an agent that monitors your supply chain, detects a delay, evaluates 3 alternative suppliers, and presents you with the best option to approve with one click. This is the ultimate peak of the AI hierarchy we've discussed. From simple data to complex agents, we've mapped the entire landscape. But theory is one thing, practical application is another. To truly master this as a professional engineer, we need to see how these layers fail and succeed in the real world. In the next chapter, we will dissect a professional case study to see how these architectural principles are tested under fire. In the field of data architecture, the biggest mistake is choosing the most hyped technology rather than the most appropriate one. When a business stakeholder asks for a solution, a professional engineer must map the problem to the correct layer of the AI hierarchy. For structured data problems like demand forecasting or credit scoring, traditional machine learning algorithms like XGBoost or Random Forest remain the gold standard due to their interpretability and efficiency. Deep learning shines when dealing with unstructured data such as image recognition for quality control on a factory line. Generative AI, however, should be reserved for tasks requiring high-dimensional reasoning or content synthesis, such as automated customer support or code generation. Misaligning these leads to architectural debt. But here is the critical question. What happens to your bottom line when you use a billion-parameter model for a problem that a simple regression could solve? Let's look at the financial implications in the next scene. From an enterprise architecture perspective, total cost of ownership, or TCO, is the ultimate filter. Implementing a generative AI solution for a classification task might cost 100 times more per inference than a fine-tuned BART model or a simple logistic regression. We must factor in GPU scarcity, token pricing, and the latency overhead of large-scale models. While GenAI offers a fast-to-market advantage for prototyping, the long-term ROI often favors the lower layers of the hierarchy for high-volume specific tasks. A professional engineer doesn't just look at the accuracy score, they look at the cost per prediction. If your inference cost exceeds the marginal profit of the transaction, the architecture has failed. This logic is what separates a researcher from a systems architect. This approach seems logical, but how do we objectively determine if a project is even technically possible before spending a single dollar? I will show you the exact checklist we use in the field. Before initiating any AI project, I apply a feasibility assessment framework that is standard practice for information management professional engineers. We evaluate 4 core dimensions: data readiness, latency requirements, regulatory constraints, and hallucination tolerance. For instance, if you are building a medical diagnosis system, 1% hallucination rate in a GenAI model is a catastrophic failure, making DL or ML a more feasible choice. Conversely, if your data is sparse but you need creative synthesis, GenAI is the only path. This checklist ensures that we don't just build cool technology, but compliant and reliable systems. This is the rigorous mindset required to pass high-level technical certifications and to lead enterprise digital transformations. Now, let's pivot from the boardroom to the exam hall. How do these practical concepts manifest in professional certification exams? In the Information Management Professional Engineer exam, the hierarchy of AI is a frequent key topic. You aren't just asked to define terms, you are asked to compare and contrast them within an architectural scenario. The top patterns include explaining the evolution of AI paradigms, the relationship between ML and DL in terms of feature engineering, and the governance of generative AI. Candidates often fail because they provide surface-level definitions. To score top marks, you must mention the shift from manual feature engineering in ML to automated representation learning in DL and the prompt-based interface of GenAI. You must demonstrate that you understand how these technologies build upon one another. But knowing the definitions is only half the battle. You must also know how to measure success in each layer. Does an F1 score work for a chatbot? Let's find out. Evaluating models across the hierarchy requires a diverse toolkit of metrics. For machine learning, we focus on statistical metrics like precision recall, and the F1 score. As we move to deep learning, specifically in computer vision, we add MAP or intersection over union. However, when we reach generative AI, traditional metrics crumble. You cannot evaluate a poem or a complex reasoning chain with an F1 score. Instead, we use linguistic metrics like BullEU or ROGE, and increasingly, LM as a judge of frameworks where a stronger model evaluates a smaller one. Understanding this transition from quantitative to qualitative evaluation is essential for any architect. This allows you to build a robust MLOps or LMOps pipeline that actually reflects user satisfaction. But even with the right metrics today, the technology is moving at light speed. What does the landscape look like 5 years from now? As we look toward 2030, the AI hierarchy is evolving into a more integrated composite AI framework. We are moving away from massive, general-purpose LLMs towards sovereign AI and specialized small language models or SLMs that run on device. Regulation will be the primary driver of architecture, with the EU AI Act and similar global standards forcing a privacy-by-design approach. We will also see a resurgence of symbolic AI merged with neural networks known as neuro-symbolic AI to solve the hallucination problem once and for all. For a professional engineer, staying ahead means monitoring these shifts in the ISO IEC standards and NIST frameworks. We have covered the case studies, the costs, and the exams. Now it is time to synthesize everything into a single, master-level blueprint. In the final chapter, I will provide the master architect's summary to ensure you never fall into the hierarchy trap again. In the world of information engineering, the most expensive mistake is architectural mismatch, using an atomic bomb to crack a nut. We have journeyed from the broad umbrella of artificial intelligence through the statistical rigor of machine learning into the layered complexity of deep learning, and finally to the transformative potential of generative AI. A true master architect views these not as competing choices, but as a nested toolset. You must recognize that while GenAI like GPT-4 or Claude 3.5 captures the imagination, the bedrock of your enterprise intelligence still relies on the structured predictability of classic ML and DL. Successful integration means placing the right technology at the right layer of the stack. For instance, using XGBoost for tabular financial forecasting while leveraging an LLM for summarizing the resulting reports. This hierarchical clarity prevents the AI hierarchy trap where complexity is mistaken for capability. But even with a perfect map of the hierarchy, where does this knowledge lead you in the broader enterprise data ecosystem? Understanding the hierarchy is only the beginning. As a professional engineer, your next challenge is operationalizing this knowledge through AI engineering and data fabric architectures. The hierarchy we discussed must be supported by a robust data foundation. Think of IBM's data fabric or the ISO ISC 3885051 standard for data governance. You need to transition from model-centric thinking to data-centric and system-centric design. This involves mastering MLOps for traditional models and LMOps for generative ones, ensuring that your pipeline handles data drifts, hallucination risks, and vector database scaling. The future of IT strategy isn't just knowing AI, it's about orchestrating it across the hybrid cloud. We are moving toward a modular world where AGI architectures bridge the gap between static DL knowledge and dynamic enterprise data. Is your current infrastructure ready to support this multi-layered orchestration, or will it crumble under the weight of unmanaged complexity? The answer lies in how you transition from theory to practice. In the field, we often see teams chasing the shiny object syndrome, implementing generative AI simply because it is trending, even when a simple linear regression would suffice. True wisdom in information engineering is found in the principle of parsimony. A master architect chooses the simplest solution that satisfies the requirement with the highest reliability. As we conclude, remember that your value is not in how many neural layers you can build, but in how effectively you solve business problems while minimizing technical debt. Whether you are preparing for the professional engineer exam or leading a digital transformation project, let your design philosophy be guided by clarity and hierarchy. Do not let the hype cloud your judgment. Instead, let the hierarchy empower your decisions. We must ask ourselves, are we building for the demo, or are we building for the decade? This mindset shift is what separates a technician from a true strategist. We have covered a lot of ground, from the philosophical why to the technical how of the AI hierarchy. Now, I want to leave you with a final, critical question to reflect on. If you were tasked with building a mission-critical automated medical diagnosis system today, which layer of the hierarchy would you trust as your primary logic engine, and how would you mitigate its inherent risks? Think about the balance between the interpretability of traditional ML and the vast knowledge of GenAI. Your answer to this defines your architectural maturity. I encourage you to share your thoughts on this scenario. Let's turn this lecture into a community of practice. The AI landscape will continue to shift, but the foundational principles of hierarchy and engineering rigor remain constant. This marks the end of our journey through the AI hierarchy trap, but your path to becoming a world-class strategist is just beginning. Keep building, keep questioning, and always look beneath the surface of the hype.